So we have a diving board with a 40 kilonewton load being applied at point B, and we know it'll bend over like that. So this is a wall, if you can't picture it. So we've got a uniform cantilever, so it's uniform. Everything that we do is uniform, isotropic, so it's the same material all the way through. It's 4 meters long. You've got a concentrated load at 3 meters in. Determine the vertical deflection at the free end. So this is at point C. And we've got two deflections. We've got delta 1, which is the distance down from point 0 down to point B, and then we've got delta 2 is where we can work out that final distance down, and this is where we start looking at our radians and what the slope is at a particular point. This was an exam question. It was the exam 2009. First thing that I would be doing is putting everything into like sort of newtons, millimeters. So we got 6, 5, 1, 2, 3, 4, 6 newtons per meter squared. So I'm going to put everything into meters and newtons. Again, this 40, it's a point load, and in books it's either a W, capital W, it can be a P. Also in some books, it doesn't really matter what it is, just so that you don't get confused. We're going to say that everything going upwards in terms of deflection is going to be positive. You find that most books will have a deflection downwards as being negative. So this is the direction of movement. We could draw a shear force diagram. So if we had our cantilever, so as we're going along our beam, there is nothing from C. When we hit B, it drops down 40. Then it carries all the way along. So that would be our shear force diagram. So we'll be designing that beam to cope with 40 kilonewtons. We could draw our bending moment diagram. So as we cover over the whole beam, we've got C, no force yet until we reach this point of 40. But at this point here, we've got 40 times by 0, go 1 meter in, 40 times by 1, 40 times by 2, 40 times by 3. So at point B, this is when we start getting a bending moment. Our bending moment at that point would be 40 times by 3. That's 120 kilonewton meters. Then in terms of deflection, so the deflection at B, what you'd have to do is just look at the back of your handout and try and find the situation where you have a cantilever with a point load. So here we've got the deflection at C is PA cubed. So we've got a distance A there over 3EI. Another chart is just could be showing that it's capital W times by L cubed over 3EI. So you got make sure you pick off the right formula. So it's going to be minus, because it's coming downwards, WL cubed over 3EI. So our W is 40, putting everything into newtons, putting everything into meters, and we're given what E multiplied by I is in the question, which is 65 times by 10 to the 6. So that's Newton meters squared. That equals minus 5.538 times 10 to the minus 3 meters. So it's coming down 5.54 millimeters at point B. So on our diagram, this is the delta 1. So at point B, we've got this it's dropped down, this delta 1, but we want to know what is the vertical deflection at the free end, in that point C. So there's B. So we've just worked out what delta 1 is. So what is this distance here, delta 2? In order to do that, we need to know what is the slope of the beam at point B. We know that the distance from the end to B is 1 meter. So we're going to end up with a triangle. Well, if we knew what the angle was, then we could work out what this vertical deflection was, delta 2. And if you look in your handout, the slope at B equals WL squared over 2EI. So we put in our values again. and that equals 2.769 times 10 to the minus 3 radians. If we multiply that by 180 over pi, we get 0.159 degrees. So this is 0.159 degrees. And then just using trig, you can find out what delta 2 is. Which is 2.8 millimeters. So the vertical, in terms of the final answer, vertical deflection at C is our delta 1, which is 5.54, plus our delta 2, deflects 8.3 millimeters.